All right. I think I got everything.
I mean, to be fair, one class contract, they said they're going to take it for him.
Well, I just don't have any class.
Ah, I see. All right. So I'll tell you guys the ever important code here in just a second, although of course it's not that important because what actually matters is the paper. But for the sake of going through the motions, and also because I know your life is more complete if you have a top cap code to put into your phone, 9493. There you go. Exciting, yes? 9493. Okay, well, contain yourselves. So here's the actual attendance sheet. If you guys could add a number to that, that'd be awesome. And I think that I had a newer one that we were handing around and must have gotten my other binder or something. Anyway, I'll begin with a word of prayer. Dear Heavenly Father, we thank you for this opportunity we have just to meet and study your creation. Just pray you'd be glorified in what we do and that we'd all understand a little bit more about physics today, Lord, from it. Lord, in your name I pray, Lord Jesus. Amen. Okay, so, example. Suppose you got a plane, all right? You got a box here, mass M, all right? And you push on that box with a force, all right, F naught, all right? And just to make things specific here, let's suppose that the mass is 50 kilograms and the pushing force is, I don't know, 300 newtons. All right? Then the question is, what happens? Now, I suppose to make this more, specific, I really should give you some kind of angle here, right? So because I usually tend, you can take the angle off wherever you want, but let me suppose I talk about it off the, angle of, off the horizontal here. So let's suppose that that's 30 degrees, all right? So if this is the situation, then we can study the motion in terms of Newton's laws, all right? And so to start with, we're going to assume that the plane is essentially frictionless, all right? In other words, we're going to ignore friction, at least to start with here. And so I can draw what's called a free body diagram for the mass. All right, so what are the forces at play here? The one force is F naught, right? But if you look at it, we can break F naught into two pieces, right? So on the one hand, you have F naught cosine 30 degrees that way, right? But we also have this piece here, F naught sine 30 degrees that way, right? Okay, what else? The other forces at play on this box are gravity, of course, right? So I can picture it up here, gravity like that, right? mg. And there's one other force which has to be here in order for the motion to be along a plane, yeah? The normal force, right? Without the normal force, we couldn't logically have the box stay on the plane. So we'll call that F sub n. If you look at some of my handwritten PDFs I have on this stuff, I've just used capital N for the normal force, but that has its own problems because of course then you've got newtons, so F sub n, no ambiguity there. All right, so we got this normal force like so, all right, and of course you got your mg like that. Okay, so some questions we can ask, like what's the normal force, right? We could figure that out. And another thing we could figure out is what's the acceleration of the box, right? So let's answer those questions. So the situation here is that the net force in the x direction is equal to what? Exactly, F naught cos 30 degrees, which is essentially 0.866 times 300 newtons, whatever that works out to, right? And so that tells me then that the mass times the acceleration in the x direction is equal to whatever that's equal to, right? 259.8? All right, I'll take it. Thank you. So that means that the x acceleration is equal to 259.8 newtons, right? Divided by what? My mass, which is 50 kilograms. So that gives me what? 5.196 meters per second squared. So there you go. That's how we would find the acceleration in this situation. Now, of course, what's the y acceleration? By assumption, the y acceleration is 0, right? Because it's staying on the plane. What's the normal force? So we know that the mass times the y acceleration is equal to 0, right? Because acceleration in the y direction is 0. But of course, Newton's second law still holds. So it's also the sum of the forces, right? And the sum of the forces here, you got your F sub n going up. If we take up as positive, which we do by default, and then we saw what? Minus F naught sine 30 and minus mg. So apparently, the normal force is simply equal to mg plus F naught sine 30, also known as 50 kilograms times 9.8 meters per second squared, plus 150 newtons. See, because sine of 30 is 0.5, and 0.5 times 300 is 150. I'll let you guys do the other part for me, though. 640. So the normal force works out to 640 newtons. There you go. Any questions? Like the principle here is we draw a free body diagram to identify all the forces, and then we break them up into two perpendicular directions to, to add vectors as appropriate. Example 2. What if instead of being on a level plane, you had the plane was at an angle? Let's say it's at angle theta. So suppose you have an angle theta plane, and you've got a box resting on the plane. We'll just leave the box on its lonesome. Just treat the box alone. We won't put any forces on it this time. What happens? And again, we're going to assume that, essentially frictionless for the moment. Okay? So what goes on here? That's right. So that's right. Fn would be like normal to the plane, like that. Correct. And there's also, yeah?
Force of gravity.
Force of gravity, which goes which way? Yeah, like that, right? So mg, directly downward. So in this situation, there's two different ways you could go here, right? You could decide, I'm going to do everything in terms of horizontal and vertical, and we could break everything into x and y components, right? That's just not very natural for inclined plane problems. Usually we're actually interested in the so-called parallel and perpendicular directions. So the normal force is, by assumption, always perpendicular to the interface. That's like essentially the definition of normal force in part. So the normal force is, already in the perpendicular direction. But gravity, we got to split up. We got to break that thing down. There's two pieces here, you see. There is a parallel piece, like so, and then there is the perpendicular piece, like this. All right, so the red is parallel, the green is perpendicular. It's in the same direction as the normal, but opposite direction, if my picture was right. Now, if this is theta, think about it, where else would you find theta here?
The green and blue.
Yeah, exactly. This then is also theta by trigonometry. All right. If you wanted to, I could extend the green line down, and then you would see that If you did that, the angle here would be complementary to theta because this is a right angle, and then that would force theta to be complementary to that angle. Anyway, you stare at it for a little bit, you'll find it's theta. So once you know that that's theta, check it out. So the blue one is mg, right? But that makes this red one mg sine theta, and it makes the green one mg cosine theta in terms of magnitude. So let me write Newton's laws here. Mass times the parallel acceleration is equal to what? So now you got to make a decision. Are we going to call down the plane positive or up the plane positive? What do you guys want? Up is positive. If up is positive, then I must put minus mg sine theta here. And I can't decide if my m is uppercase or lowercase. Let me go back to uppercase since I started. Mg sine theta. There you go. How about the mass times the perpendicular acceleration? What goes on there? You got the normal force, which we're going to take up. We're going to take that to be the positive direction, all right? Which means that the green part of the gravity, the green vector component, the perpendicular component of the gravity to the plane, is minus mg cosine theta. Does that make sense? Now, in this situation, we dispense with, so typically, since the acceleration, right, is just going to be equal to like, well, let me just say this. The magnitude of the acceleration is equal to a parallel. Because the perpendicular acceleration is by assumption 0 in these kind of situations, right? So usually what I do is I don't even write a parallel. I just write a here. And I just let a be the acceleration parallel to the plane because the motion is one-dimensional. So it's not, one-dimensional in the sense that all the motion's along the plane. So let's just adopt that convention as usual. We'll just say that for this kind of problem, the parallel direction is A, all right? Now, I am not a stickler for up the plane always being positive. You'll just have to pay attention to the given problem. It might be that I declare down the plane to be the positive direction. It just kind of depends on what's more natural for the setup. But just warning you, we pick a convention, you have to be consistent with it in a given problem. That much is true. Okay, anyway, so to summarize, for this particular problem, we've got m times a is equal to minus mg sine theta. And we also have that the normal force is equal to what? Mg cosine theta. In this particular situation, there's no pushing force, right? Are we in agreement so far? Do these formulas make sense? Like, let's check some exceptional cases. First of all, divide by m. What do you get for the top? What's the acceleration? Minus g sine theta, right? What happens to the plane when theta equals to 0 degrees? What happens? The sine of 0 is 0. Does that make sense? Should the box slide down the plane if the plane isn't inclined? Hopefully not, right? Like, it would be really weird if you were just looking at this and all of a sudden it just started, That'd be weird. That doesn't happen. On the other hand, if I can figure out how to work this thing. It probably doesn't.
There's pins and
There's pins. Watch, I'll pinch my fingers here. Something fierce if I'm not careful. I'll get it eventually. On the other hand, of course, if we do this, that happens, right? Now, there's something else that's going on there, which is what? Friction, right? Now, if you could imagine I can't quite demonstrate it, but if well, maybe I can. Oh, thanks. There we go. Check this out. What do you know? What happens when you put theta equal to 90 degrees? Sine of 90 is 1. The acceleration is? Minus g, right? My point to you is a small point, but as you're setting up physical problems, you should always think about these kind of exceptional cases to check yourself, right? Anyway, man, it is a mess up here. Look at this. Ah. Just a second. There, better. Next up, what if we pushed on this box? So example 3, suppose you've got the inclined plane, right? Angle theta, and you've got the box sitting here, right? And suppose you just pushed on the box to make things relatively simple. Let's suppose you push on it with angle F0 horizontally. What would Newton's equations look like in this situation? So in this situation, I got to think about how to break my pushing force, which I'll make a little bit longer here for the sake of my picture, into two pieces, right? You can think about the pushing force. I can break it into a parallel piece, like this, and a perpendicular piece, like that, yeah? And alternate interior angles says this is theta, which makes this F0 cosine theta up here, and that makes this F0 sine theta over here. Now the normal force in gravity, same song and dance as my last example, right? So I can still say, oh, okay, so I've got mg sine theta. Is that right? You guys tell me, is that right? It's perpendicular, it should be the sine, right? Wrong. This is cosine theta. The sine theta is the one that's parallel to the plane. Be careful. That's a very popular mistake in this material, to switch the sine and cosine there. And then, of course, the normal force. See, the problem with a problem like this is it gets awful busy awful fast. All right, so let me draw it again here. We got the normal force. We've got F0 sine theta. My bad. Which way does F0 sine theta go? Down, right? No, it goes normal. F0 sine theta is it's normal, but it's down. It's in the same direction as this here, this mg cosine theta. Is that it for the vertical pieces? For the perpendicular pieces? Normal force up, pushing force down, gravity part of gravity goes down, perpendicular plane. All right, I think that's it. Now here we have F0 cosine theta, that part of the pushing force. All right. And what else goes on? You got your mg sine theta like so, right? I think that's it. If there's no friction, that's it. Okay? So then what are Newton's laws here? So the acceleration perpendicular is still 0, right? So the normal force minus F0 sine theta minus mg cos theta, that has to be equal to the mass times 0, right? Because the perpendicular force is 0. In other words, we can find that the normal force here is what? Normal force is equal to F0 sine theta plus mg cos theta. By pushing on the box, we have increased the normal force by that much. Okay? Now, again, if theta is 0, that pushing force doesn't mess with the normal force at all. Does that make sense? Think about it. If theta is 0, you're pushing horizontal to the plane. You're not going to affect the vertical force on the box. It makes sense. This formula does. On the other hand, we have mass times acceleration is equal to F naught cosine theta minus, I'll at least try to keep with the same conventions here for 2 examples, right? MA F naught cosine theta minus mg sine theta. There you go. This would tell me that the acceleration in this situation would be F naught over m cosine of the angle minus g sine theta. So there would be the acceleration of the box in this situation. All right. Now, so you could do lots of examples like we're doing at the moment, but oftentimes there is something called friction, right? So we should talk about that. So let's talk about it. Friction. There is something called static friction. The force of static friction is equal to mu sub s. Well, I should say it's less than or equal to mu sub s times the normal force. So the force of friction max in the static case is mu sub s times the normal force. So static friction, for example, if I just stick it like that, what is the force of static friction right now on that? 0. So it could be 0. And then it could be anything up to a certain point, all right? Right up until I put enough that it starts moving. Once it starts moving, then you're in the kinetic regime. And so for kinetic friction, we have the force of friction is just equal to mu sub k times the normal force. So kinetic friction is, constant. So a graph of it would look something like this. If we graph, let me see if I can make this graph. Force of friction this way, normal force that way. All right, so like what goes on is basically you've got, 0 friction force up to some point, all right? And that would be like, mu sub s times Fn. And then it drops back to, see, this is not the right graph. I'm going to bail on this. Dr. Sprano taught me that. See here? So, yeah. I've been telling the wrong jokes in here. Man. Let me try another one. Example 4. So let us suppose that we push on the box with a force of F naught this way, horizontal, all right? And let us suppose that the mass of the box is 100 kilograms, all right? Okay. If the coefficient of static friction of the box plane interface, let's say, is 0.6, all right, what is the minimum F naught needed for the box to move? So I made it super simple for us, right? In the sense that, what's the normal force in this situation?
It's equal to mg.
It's just equal to mg, right? There's no other polluting contribution from the pushing force. Like, so the situation here is, well, let me just draw it down here. So if we think about the box, we got normal force acting up. We've got the force of gravity acting down. We've got the pushing force going like this. And then the other thing I haven't described yet for friction, but this should sort of be obvious. What direction does the friction force point? Opposite the direction of motion? See, that doesn't work because it's not moving. So, yeah. Opposite to F0 is correct, but can we describe it like more generically? Like it's generally opposite the direction of potential motion, right? So like, but yeah, opposite F naught is exactly right. You're correct, sir. So the force of friction goes like this. All right. I will now solve the rest of this problem in the style of a certain fictional genre. Cook. Cook, cook. Cook, cook, cook. Cook. Cook, cook, cook. Cook, cook, cook. Cook.
You're a Pokemon, aren't you?
Cook. Yes. Cook, cook, cook. Oh, I'm sorry. I broke character for a second there. I should have said yes. My bad. Yes, that's how you do an example in the style of Pokemon. So I made this joke years ago. I forgot about it. A student told me they were still talking about it. I was like, what? I don't even remember that. I should bring it back. So there you go. Anyway, so the normal force is mg, right? And that makes, okay, so what, and I need to think about this a little bit more. What, if it's not moving, what's the acceleration? Zero, right? So this is also 0. So we'd be looking for F naught equals to the force of friction, which is what? Mu sub s, which is, less than or equal to 0.6 times mg. So if F naught is less than, well, let me write this a different way. F naught minus the force of friction is equal to F naught minus mu sub s times Fn, right? But mu sub s times Fn we can write as what? Mu sub s times mg, right? That is the difference between the pushing force and the force of friction. There comes a point when that has to be positive, right? If F naught is greater than, so like this is, let's see here. This when I write this equality right here, right? Actually, this one right here, this assumes what? Max friction force. Does that just, because the friction force can be 0 up to that value. So in short, the answer is if F naught is like greater than or equal to 0.6 mg, that means it moves. All right, once it's, yeah.
Would it move if it was equal to? Because I thought the static friction force.
If it's exactly equal to it, it's like an unstable kind of thing. Just a little, will start it moving. And then once it starts moving, it's in the kinetic regime, which means it starts moving faster. Because once you break the static weld, like it's easier to move something. You guys have done this, right? If you're moving something heavy, once you get it going, it's easier to keep it going, right? That's not just momentum, whatever that is. It's also has to do with the fact that for actual physical substances, ignoring some weird stuff like non-Newtonian fluids, generally speaking, like, friction is less than mu s for most materials. All right. So anyway, interesting related question is something like, and I don't know if I have time to work this at the moment, but let me check. 10 minutes. Yeah. a little iffy. All right, well, I'll give it a go. So suppose we put a box on a plane, right? And like this one. And we have friction. All right? Then the question is, at what angle will the box start sliding? Right? At what angle will the box start sliding? So, example 5. So inclined plane. We won't put any pushing force this time. We'll just be up against gravity. All right? And so here, mu sub s, coefficient of static friction. And I won't even tell you the mass of the box because we don't actually need to know it. All right? So mass m. And the question is, at what angle theta are you just going to start sliding? All right? Let's work it out. So what's at play here? Well, your force of friction better be going this way, right? Your normal force better be going that way. You got yourself mg sine theta this way, and you got mg cosine theta that way, according to the picture I just erased. But it's the same thing every time, okay? In that regard. The breakdown of a pushing force or a pulling force, you've got to pay attention to the details of the problem. You can't just copy what I did in that example down and expect it to make sense. Like the particulars of the geometry of a given pushing or pulling force is given to you have to be digested and the trigonometry has to be addressed. But this one, I think that's it. Okay, so what goes on here? The normal force is mg cosine theta, right? Which means that the force of friction, max, is mu sub s mg cosine theta, right? And then we can look at the Newton's second law parallel to the plane. Ma is equal to force of friction, which is mu sub s mg cosine theta, minus mg sine theta. By the way, if we were past, while we're at it, what if we were in the kinetic region? What if the box was sliding? What's the difference? If it's sliding, you just have this, right? Ma is equal to mu sub k mg cos theta minus mg sine theta. So the same force law and everything. And you can see then that the acceleration, if it was sliding, would be given by a times the kinetic coefficient times g cos theta minus g sine theta. So there you go. That's the acceleration in the situation that it's sliding. But what's the condition if it's not sliding? Like that acceleration should be what? That should be 0, right? So we don't just have this. In the case, in the borderline case, we have that equals to 0, right? In the theta max case, right? And so what does that give us? Oh, the masses cancel, don't they? See that? Divide by m. Got nothing to do with the mass of the box. And so that gives us that mu sub s, and we can divide by g. All right? Divide by mg, in fact, and make the equation weightless. So mu sub s cosine theta minus sine theta equals to 0. Lo and behold, mu sub s is equal to the tangent of theta. So the answer is that the maximum angle you can get away with is inverse tangent of the coefficient of friction. If you go and look at like a table of coefficients of static friction, you'll see that they're less than 1. Okay? So what that means is, like, hypothetically, best case scenario, inverse tangent of 1 is like the biggest angle that you can get away with not sliding, which is what? 45 degrees, right? So like at 45 degrees, anything past 45 degrees, everything should be sliding. Unless there's something more than just friction going on, like some kind of like rigid attachment. They're not just, of friction. Now, friction, of course, is like it's a macroscopic model of a very complicated microscopic thing, right? What friction's coming from is, of course, the two materials, like the peaks and valleys of their molecular substrate, like ripping past each other, right? And the way those two things interlock, that somehow macroscopically gives you these formulas. But that's, you know, these are approximate rules that work pretty well for, you know, reasonably slow. They work when they work, but they don't work always, is what I'm trying to say. Okay, so anyway. But that's how you work problems in here with those. So. By the way, I'm about to run out of course notes for you guys. I'm hoping to type up some more. I'm trying, but a little short on time too. I don't know. We'll see what happens.